All right, so this week we're going to talk about test automation. So last week we talked about our model-driven test design. We talked about our categories of activities, right? We had the test design activity, we had the test automation, test execution, test evaluation. And I said that we were going to be spending most of the semester. I'm sorry? I'm sorry? Okay, maybe that wasn't for me. All right, so last week I mentioned that we were going to be spending most of the semester up here in test design. But first this week we're going to take a detour here into test automation and kind of give us some of the mechanical skills that we need to be able to implement tests and implement automated tests so that we can go back and then effectively do something with test design and be able to actually write some tests as a result of the tests that we design. All right, so what is test automation? Pretty simply, we're just going to be using software and automated tools to control the execution of the tests, to compare the actual outputs to what we have said the predicted outputs are, set up preconditions, basically control the execution and the data collection of our tests. Now notice I did not say here, create the input test values, right? That's actually a test design function. Although during test automation, we'll be taking those input values and we'll be building them into the automated tests. So why do we want to use test automation? First, it reduces cost, right? If we can run tests on an automated basis, we can run them more quickly. We need less labor to do it. It's less expensive. It also reduces human error. If we're doing tests manually, there's a significant chance that we're simply going to make a mistake and we're going to get the test wrong and get a bad result out of the test simply because we made a mistake executing it. And that's related to this third thing, right? We can have a variation in test quality. If we've got different people running tests, they may be running it in slightly different ways. They may have different timing. They may do things in different order. They may skip steps. They may think they know better than what the test instructions say. And we can eliminate all that with automation. I'm going to jump to the bottom one, because while everybody likes to focus on the first point here, oh, if I automate the test, right, that's going to save time and money. And that's true, but that's not really the big benefit. The big benefit is this last one. Instead of manually doing a test once or twice and then saying, well, I could automate that and then I can run it faster for those 1 or 2 times. Okay, that might be a benefit, but it's a small benefit. The big benefit is I'm not going to run it 1 or 2 times. I'm going to run it 100 times or 1,000 times or 100,000 times, right? I'm going to run it every night for the duration of the project. So we're going to get a lot of value out of the tests by constantly checking our system to make sure that no errors or defects have crept into it. So, what's the outlook for test automation? And, hey, here's another good class participation opportunity because I'm trying to get a comic from Dilbert or XKCD or a PhD comic or something, trying to find a relevant comic for each, for each topic. So anywhere along the way in the class, if you've got one in mind, some kind of relevant comic, let me know. All right, so the upper graph here, the idea here is it's taking me a certain amount of time to work on the additional task, and hey, I'm going to automate it. So I'm going to spend a little more time to automate it, and then it's going to take way less time. And then the joke here is that, well, really what happens is that the effort of automating, kind of takes over, and I'm spending so much time on the automation that I don't have any time for the original task anymore. That's not entirely false. So that's something you need to manage, right? You need to actually carefully select what you're going to automate and how much time you want to spend automating it. And there are a lot of tests where automating it just doesn't make sense. I was recently working with a project at my company, and they were working on a video viewer, basically, that would take airborne UAV video And one of the tests that they had was they'd have the video that was taken by the airborne camera in one window, and they'd have a moving map display in the other window of where the UAV was at the time. And that seems straightforward, right? I want to know where the thing is, I want to know where the camera's pointing, and I want to see what the camera's pointing at. That's fairly easy for a person to do, right? It's fairly easy for a person to look at that and say, oh yeah, that all makes sense, that looks good. And they asked me how they should go about implementing it. And how would you possibly automate that, right? How would you be able to match what the video is with what's on the map? I mean, that would be an incredibly difficult thing to automate, but it's a thing that people are actually pretty good at. So my advice to them was, yeah, don't automate that, right? Don't even try. So testability. When we're looking at software, we want to consider the software testability. That is simply the extent that the software allows itself to be tested. And I know that sounds a little bit silly, but think about, for example, probably in your undergraduate computer science education or similar, you were probably taught about encapsulation and data hiding and object-oriented programming and how all of these things that are necessary to be should be private, right? And all your data objects should be private. They should all be encapsulated and hidden inside your class. And there are good reasons to do that. And that is the absolute enemy of testability. If all of my internal data, all of my internal state is private, and I have no good way to look at it, how can I really test that thing? I mean, I can exercise it, but then if I'm not able to inspect the internal state, how do I know that it worked? So testability is often, is often counter to what you would in theory like to do for things like encapsulation and data hiding. So we want to try to prioritize our software design to prioritize things like maintainability and testability, possibly prioritizing those over the theoretical advantages of, nice pure software, right? That looks really good from a, from a data hiding, from an encapsulation perspective. So testability is dominated by two concerns. The first is, how easy is it to provide the desired test values into the software? And the second one is, how easy is it to observe what the software did? So those are controllability, right? The controllability concern is, how easy is it for me to provide the software with the test data that I've identified? And often that's easy, especially in unit testing. In unit testing, it may be as simple as, well, I'm just calling this method and everything I need to do is in the argument list, so I can just set it all up in the argument list and send it in. That's very easy controllability. But you might have something different. I come from a real-time embedded systems background. So imagine some kind of system that's a filter, right? And it's taking in data, and then it's considering the last 10 or the last 100 data points that it saw in order to construct what its output is. So now controllability is a little harder. I can't just call it once. I have to call it 100 times with a carefully controlled set of inputs in order to verify that what my output is correct. And then the corollary to that is observability. And in observability, we're just thinking about, how easy is it to see what the software did? And again, we can have very simple methods, or very simple functions that I give all of the inputs on the argument list. That's very controllable. And then it returns a value. That's very observable. On the other hand, again, with something more complicated, if I've got a big filter, or if I've got some kind of tracking system, it's taking in GPS inputs and trying to figure out where you really are. How easy is it to observe that? At any point, can I look in there and can I actually see what the current state is? And can I use that information to make a judgment of whether it's working? Sometimes not so hard, not so easy to do. And as I was hinting at in my previous slide, as we increase abstraction, as we increase our abstraction, and as we increase things like, you know, our data hiding, our encapsulation, we tend to be reducing both controllability and observability. So we need to be trying to strike a balance between all of those things in our software. So there are some other things that can affect that. We can have prefix values. And prefix values are those that, while they're not necessarily the inputs that I want for this test, they're a set of inputs that I need in order to get the system into the right state so that I can run this test. So perhaps I wanted to test in a car, I wanted to test the anti-skid braking system. So what do I need to do? Well, we need to step on the brake and then see what happens with the wheels. But that's not good enough. First, I need to get the car up to speed, and I need to get it on a wet surface, right? There are other inputs that I might need to get the car into the right state where I can now apply the brakes and make sure that it does what I want it to do. We can also have postfix values. After the test is conducted, how do I get the data out? It may not be as simple as a return value. I may need to make additional function calls. I may need to cycle the software through additional functionality in order to make sure that the end state of my test is what I wanted it to be. So when we look at a test case contains several different things. A test case contains all of the input values necessary to complete the execution, right? And that's the specific test values as well as any prefix values that are needed to get the system into the state that we want it to be in when we actually execute our specific test. And then we also have expected results. A test case without expected results, right? If I'm not making some comparison that checks that the software did what I expected it to do, then my test is almost useless, right? Without expected results, all I'm doing is being able to say, well, it didn't crash. And okay, it didn't crash, that's good, but I mean, that doesn't tell us very much, right? So I have to have that set of expected values on the output. So we can put that together to make a test case. The test case contains the prefix values, the test inputs, the postfix values, the expected results, everything that's necessary for the execution and the evaluation of the software. And then when we roll those test cases together, we can take many test cases and put them together into either a test set. Some people call it a test suite. I don't care either way. Those terms are equivalent as far as I'm concerned. You can use whichever one you like. And that's just a collection of different test cases, right? So we checked that 1 + 1 is 2. That was a test case. And we checked that 3 + 5 is 8. That's a test case. And when I put those two together, and probably a bunch more, now I have a test set that tests a whole bunch of different addition values. And then I can build myself some kind of executable test script. And this is the automation portion of it. This is where I have some kind of prepared executable piece of software or inputs to some tool that will actually conduct the test and collect the results. And supporting all those things can be a testing framework. And a testing framework is usually a software tool that has some concepts, some tools, right, that allows me to do this without having to work everything up custom on my own. And there are a ton of test automation framework tools out there. JUnit is very common. That's a test automation tool for Java. It's open source. It's used by, seriously, millions of people. It is by far the most common and most popular test framework for Java. For C++, there's Google Test and literally hundreds of others. I've used 5 or 6 different unit test framework or test frameworks, test automation frameworks for C++. I've kind of settled on Google Test because it's pretty well supported, it's got good capabilities, it's got good documentation, and it's really easy to jump out to someplace like Stack Overflow and get information to solve any problems that you might be having because it's used by a lot of different people. Microsoft and Visual Studio, they include MS tests for C# and some other languages. There are some very sophisticated commercial products like VectorCast. VectorCast is a test framework. It supports C++ and Ada, for those of you who are familiar with the language Ada. And it's really tailored towards embedded real-time systems. Then there's Cucumber. Cucumber is written in and supports various languages. It's also open source and free, which is nice. And Cucumber is used not so much at the at the unit testing or the integration testing level. Cucumber is used more at the system testing level. And we are going to spend most of the semester working with JUnit. We're also going to touch on Cucumber a little bit this week. So what's JUnit? I mentioned open source testing framework for Java. We can use it to write and run tests in a repeatable way. So it gives us a structure for writing test drivers. It gives us a set of assertions that we can use for verifying that the results are what we expected them to be. We can organize things in test suites. We can execute JUnit tests through, through some built-in provided things. We can run them standalone. We can integrate it with Eclipse. We can integrate it with other IDEs and other test tools. So it's really widely used in industry. As I mentioned, it is almost certainly the most commonly used test framework for Java. So where in our test, our V-shaped software lifecycle, where is JUnit useful? And mostly it's useful here kind of at the bottom of the right side, right? It's really good for unit testing and it's pretty good for module testing. And I could see using it for some integration testing. And as we start to get up into system testing, it's really not well suited for that because JUnit tests tend to be written to interact directly with the class or the functions that you're testing, right? You link them in. I know it's Java. We don't really link in Java, so forgive me for the terminology. But we're basically hooking up our JUnit tests directly to the class or classes that we're testing. And that works well at unit test and module test and small scale integration test. But that's not really a model that works well at system testing and acceptance testing where we're trying to run the whole system together. So what can we use JUnit to test? Definitely an object or parts of an object. That's easy. We can write JUnit to test individual methods. We can certainly write JUnit tests to look at the interaction between several objects. That's pretty straightforward. As I mentioned, pretty much intended for unit and integration testing, not really a system testing tool. Each test that we want to execute, we will implement that test as a Java method. So if we have some class, some class A that we want to test, we're going to write another Java class and use JUnit to run that Java class. And each method of that test class that we just wrote will be one unit test that will test some aspect of that class A that we're looking at, that we want to test. So Java or JUnit, open source, JUnit.org. You can download it, jam it into Eclipse or probably NetBeans or whatever else you like to use. So when we're writing tests with JUnit, we're going to grab the methods from this JUnit.framework.assert class. There's good Java doc in there. It gives a complete description of the capabilities. I'm going to talk about a few of them here. Each method that we write in that test class is going to use an assertion to determine whether that particular test passed or not. And there will be a test runner that's kind of orchestrating the whole thing that will collect the results from all those assertions to be able to say, yes, the test passed, or no, the test failed, and here are the particular assertions that did not, that failed. When we're writing JUnit tests, all of those test methods are void functions. We'll get to an example in a minute. And then I wanted to touch on just a few JUnit assertions. So when we're using assertions, what can we test for? Well, we can test that some expression is true or that it's false. A really common thing to do is to test that some expression is equal to some expected value. Or if we're doing floating point comparisons, hopefully you remember from your earlier computer science or software engineering training, we try not to test floating points for equality, right? Don't test floating point for equality. Test whether they're really close. And so a certain year allows us to do that. We could say something like a certain year, 3.0, some expression, and then the delta is like a plus or minus. So I could say maybe 0.1. And so if the expression evaluates to 3.0 plus or minus 0.1, then it passes. If it's outside of that range, it fails. We can assert that some expression is null or that it's not null. Or in some cases, and this can be surprisingly handy, we can just outright fail the test, right? If we execute this fail statement, it'll just fail the test. And then all assertions can take an optional first string that will be printed to the output if the assertion fails. So what's that look like? Let's take a look. So here's this class calc. It's got a public function to add two integers, and it returns the sum of those two integers. So if I wanted to write a test for that, I would write myself a new class. By convention, usually we'll name the test class, whatever the thing is we're testing, with test on the end. So if I'm testing class calc, I'll write class calc test to do it. You don't have to name it that way. There's no requirement for naming. That just makes it really easy to look at your test classes and understand exactly what thing they're testing. So then we have this @test annotation, and then a public void function, and then we'll name our test. And we can name the test whatever we want. And then we'll have some assertion in here. And this is a very simple test. So all we're doing is we're asserting that when we call calc.add and pass it 2 and 3, the result will be 5. And if that's not the case, then print out calc sum incorrect. All right, so we've got an expected value, we've got our test case with our input values, and we have an optional string to print out if the assertion fails. So to wrap up our test cases, we can use JUnit test fixtures. And so what a test fixture allows us to do, if we have a complicated test setup, say we need to create a bunch of objects and set various values in different ways and lots of prefix stuff that we need to do. If the prefix work is the same for every test, then we can take that prefix stuff out of the test and put it into an @before initialization. And so before every test, it'll do all that prefix stuff. And then if we have postfix things to do, things to clean up, reset the state of the object, whatever we might need to do, we can roll those all up into an @after function and cause all of those things, all of those postfix cleanup things to happen automatically after every test. This is not a big deal, right? It just gives us an opportunity to write those things once instead of writing them in every test. And you can choose to do initialization and resets before each test and after each test, or before all tests and after all tests, or both. All right, so now let's dive into looking at an actual testing example. So here we've got this class min. What's it going to do? It's going to return the minimum element of a list. So here's the code for min. So we're going to give it some list, and it's going to look at the list. If the list size is 0, it's going to throw an illegal argument exception. If the list is null, it's going to throw a null pointer exception. Otherwise, it's going to iterate through the list. If the first element is null, it's going to return a null pointer exception. And then it's going to iterate through the list and basically do a comparison of each item in the list with the previous known smallest item. And when I say smallest, I mean with respect to whatever comparator we've given in this class. And then ultimately at the end, it's going to return the smallest version that it found, or the smallest item that it found. So if we wanted to write tests for this, and we're going to approach this in just kind of an intuitive way, right? We're not going to use, right now for today, we're not going to apply any test criteria. We're going to just approach this in an intuitive way and think about, all right, well, what do I want to test here? So let's walk through that. So as we're building our test class, right, we had min, so now we're probably building a class called min test. What do I need to do? Well, I need to import some things, right? I need to import assertions. I need to import JUnit. We'll import java.util. That gives us iterators and things like that. I'm going to create some private list function or some private list object. This is going to be the thing that I'm operating against. And here I've chosen to create a list of strings. I could do a list of other things. I could do some other data structure. As long as that data structure supports things that are comparable, I could use any data structure I want. I've chosen here, just kind of for simplicity, to use a list of strings. Now I'm going to do a setup call here. So at before public void setup. This is a function that's going to run before the tests execute. And what's going to happen here is it's simply going to set list to be a new array list of strings. All right, it's empty, but now I have a new array list. So every time I'm running a test, that test starts with a new empty array list of strings. And then I'll add a post test, right? Some postfix stuff. And what am I going to do here? Well, I'm just going to take the list and I'm going to set it to null. That's going to cause the Java garbage collector to take whatever it was pointing to and throw it all away. This is not particularly useful, right? That would happen anyway when we exited the program, so it really doesn't matter that much. But I put it in here just kind of for example. So now let's look at the actual code and start thinking about what do I want to test and what would those tests look like? So sure, we'll just start at the top and we'll kind of think our way through it. So the first question here, that the first thing this code is doing is looking to see if it's a null list. Then it's going to look to see if it's an empty list. And then what else can control things? Well, a null value in the first list element, that might make it do something different, whether that's true or false. So that seems to be a good kind of test to have. What about this iterator? Well, if there's only one element in the list, then we won't iterate at all. That seems like a good test. And if there's more than one element, then we will iterate. So we should probably test both of those cases. So what if the next thing we pull out of the list isn't comparable to the first thing in the list? That should throw an exception. So we should test that kind of case. What if that later thing we pull out of the list is null? That'll cause a null pointer dereference behavior here. So that's a case we should test. Here's where we're doing the comparison and we're saying, well, if the new thing is less than, then let's make that the result. Otherwise, let's keep the old result. So we should test both of those things. Do we keep the previous result or do we replace it with a new result? So just kind of intuitively looking through this code, those are some points in the code that we can identify that make us think, oh, that seems like an interesting thing to test. So let's go ahead and implement those tests. So how do I test? First of all, how do I test a null list? So I'm going to write myself, right? We're going back over into our test class, our JUnit test class, and I'm going to write a test. So that starts with the @test public void. That's how they all start off. Then I'm going to name it. I'm going to just name it something that reflects what I'm testing. I'm checking for a null list, so let's just call it null list, right? Test null list. So I'm going to take my list that was set to an empty array list of strings in the setup, and I'm going to get rid of that. I'm going to reset my list to null. And then I'm going to try to call min.min and pass it the null list, and I expect it to throw a null pointer exception. So I'm going to catch that null pointer exception, and if I catch the null pointer exception, we're good. We can return this test is done. If I don't catch a null pointer exception, that's a problem because I expected it to throw one. So I'll add this fail at the end, and I'll say, well, if you don't catch the exception and you actually get out of there, then we're going to fail, and we'll just print out null pointer exception was expected. And when we see null pointer exception expected, that text will help us understand what went wrong.
Professor, I had a quick question on this test.
Sure.
I guess I was under the impression that generally a JUnit test required some assertion or some assert statement, but there's not one in this case. So in this case, pretty much, if it just returns, then the test is basically annotated as passing.
So there is an assertion in this, but it's a little bit hidden because the assertion is here in the fail statement. So basically, we're using the test logic. This, if I wanted to rewrite this as an assertion, I would just say, assert true, true, right? Because if I get here, then I want to fail. And if I don't get
okay, I
here,
get it. That's just a better way of writing what you said there. I've seen assert true used in the past, so I think
you could certainly do that, right? You could certainly do that. But here, that fail is itself an assertion, a very special case one that will just always assert itself.
Got it. Okay.
So what about testing an empty list? And this test is going to show you something slightly different. Here, we already have an empty list because our prefix code said list equals new array list string, right? So we know we have an empty list. We're just going to use it as it is. And we're going to call min.min with an empty list. And what do we expect to happen? We expect it to throw an illegal argument exception. How do I know that? Well, I could go back a few slides to the header, which told me what the desired behavior was. I could have written this test in exactly the same way as the one before, right? I could have put min.min in a try. I could have used a catch. If the catch catches the exception, I could return because that's a pass. Or I could write it a little differently. I can use this at test expected equals. And this is a handy way to write a test when I expect the test outcome, right? The desired result is an exception. This is also an implied assertion, right? This is basically saying I'm asserting that the result of this is that an illegal argument exception happens. Of these two, I find this second one a little easier to look at because this first one, you're kind of like, okay, so I call this and then I'm catching stuff and then I'm failing and wait, I'm confused because usually if I catch an exception, that's a problem, but here I'm failing if I don't. And you kind of have to think a little hard about what the logic is. This notation, I think it makes it very easy. I'm expecting this test to throw an exception. If it throws an exception, it passes. If it doesn't throw an exception, it fails. So here we wanted to test the case where the null value is the first element of the list. In that case, we expect min to throw a null pointer exception. So I'll use this expected equals null pointer exception again. And so here we'll take our empty list, which was reset for us, right? That at before gives us an empty list going into each test. So we'll take that empty list, we'll add a null into it, and then we'll add something that's not null. And so when we call min.min, it should execute that part of code that checks that first element of the list, that's a null. It should throw a null pointer exception, and that's what we are expecting as the outcome of the test. We can check a list that has one element, right? This was kind of an interesting special case that we looked at, right? What if we pull the first element off in the code and then we go into an iterator loop? Well, what if we never do the iterator loop? What if we skip over it because there was only one element? Here's that test. We're going to take list, we're going to add one string, we're going to call min.min, and here, kind of for the first time, we're using a traditional assertion. I put in foo, and my expectation is that foo is what's going to get returned as the minimum value from that list. And so if object that's returned here is equal to foo, great. And if it's not, then we'll throw it away. One thing I'll mention about this test, it works. This test works, but is possibly not the best way I could have written it. Because testing the string foo against another string foo, this works only because the Java JRE will reuse string constants. So really what this is doing is making sure, I'm pretty sure that this is making sure that the objects are the same. So maybe another way to write this would be to say assert true obj.equals foo. And then I'm explicitly making sure that I'm testing the string values rather than testing that they're the same string object. And maybe assert equals does check for strings. Maybe it does check string equality. I'm not sure. The fact that I'm not sure makes me think that writing it with a dot equals would be a better way to go, because then I'd be sure what the test was doing. So we wanted to have a test that looked for a list with elements of incomparable types. So here I can't use my list of strings anymore, because if I have a list of strings, I can't put a non-string in there. So I have to redefine list, and I have to just call it a new array list of generic types. And then I can stick in a string and stick in a string and stick in a, I guess that's actually a long. And then I can call min.min, and my expectation is that it's going to throw a class cast exception. That's what I want it to do. If it throws the exception, the test passes. If it doesn't throw the exception, the test fails. All right, so test 6 of 8. We wanted to test a list of multiple elements that had a null value somewhere later in the list. So I can still use my string list, my list of strings that was defined in my at before, and I'll add a string, and then I'll add a null, and I'll call min.min, and I expect that it will result in a null pointer exception. Number 7, we want to test a list with more than one element where we're always keeping the previous result. In other words, where the first element is the minimum value. So I'll stick in bar and foo bar, and I'll call min, and then I'll assert that what comes out of min is bar, right? Is the lowest, and it's the first thing that I put in. Then our last test, we want to test a list that has more than one element that causes us to actually exchange things, because the first one isn't the lowest. And so here I'll just reverse the order, right? I'll put in foo, then bar, then foo bar, and I expect that bar will come out as the minimum. So there's a reasonable set of, tests based on an intuitive approach. Interesting thing to look back on here. We identified 8 tests. 5 of those tests expect us to throw exceptions. And only 3 of those tests are testing what we would normally consider, kind of normal execution, the way the thing normally would work. And this is important to recognize, because when you're writing tests, it's really tempting and it's really easy to focus all of your test effort on what you think are normal tests, the way you expect this thing would normally be used. But the fact is that there's often more test cases checking abnormal cases, or special cases or corner conditions. So often spend more time checking for exception cases or failure cases than you do testing for normal or happy path cases. I'll use the phrase happy path or happy path test case pretty frequently throughout the semester. And all I mean by that is, kind of a normal situation, right? If I have this min class where I give it a list and it returns the minimum thing, a happy path test would be giving it a bunch of valid values so that it can give me the minimum of them. That's a happy path test. If I had, my earlier example that added 2 numbers, a happy path test would be giving it 2 good numbers to add instead of giving it null or empty string or something that isn't a number. Okay, so, I had this plan to just take a short break here, but I think we're coming up on 6. So I think let's just push through here this second part. Then we'll take a break before we go into the exercises. So I want to briefly talk about parameterized tests in JUnit. Now, I know that this is a lot to absorb at once, and you're probably not gonna, if you're not familiar with JUnit, you're not going to come out of this lecture a JUnit expert. And JUnit can do a lot of things, but what I'm talking about here today are really the only things we care about it doing for the purposes of this class. So parameterized tests. Imagine we've got tests to run, and we want to make the same function call lots and lots of times with different data. The adder example that I gave before, right, where we have an add function and we want to pass it 2 numbers and check the result. Well, I don't want to call that with just 2 and 2. I want to call that for many, many, many different values. But I'd rather not write a whole at test public void add 2 and 2, right? And then have assertions and everything. I'd rather not write a test method, a test function for every possible value, because then I've got hundreds or thousands of test functions that all look the same except that their numbers are different. That seems silly. There's got to be a better way. Turns out there is a better way. That's what parameterized testing does. So in parameterized testing, I'm going to have this special annotation at runwith parameterized.class. That tells JUnit, this isn't a regular test. This is a parameterized test. And then I'm going to create member variables that will hold all of the test inputs and the expected output. So my test inputs are I and j. My expected output is sum. Then I'm going to create a constructor for this class. And the constructor is going to take those inputs and outputs as arguments and is going to store them in the member variables. And then I'm going to have an at parameters section that defines the values that I want it to use. And every set of values that are in here will result in the test being called 1 time. So here I've got an array of numbers 1, 1, 2, right? And that's going to cause the test to be called once with I equals 1, j equals 1, sum equals 2. Then I've got this next set of values, 2, 3, and 5. That's going to automatically cause the test to be called again with 2, 3, and 5 passed in. And I can make this list as long as I want. So I could have hundreds of test cases on here, right? 1, 3, 4, 1, minus 1, 0, minus 1, minus 1, minus 2, right? As many addition cases as you want, you can put into this list, and it can be arbitrarily long. And what's going to happen is this test method is going to be called once for every collection, for every set of objects in that parameters list. So a really handy way to use one set of test logic with lots of different sets of test values. The other thing we'll briefly talk about here today, we're not really going to go into this too much, but I want you to know it's out there. And that's JUnit theories. Now, before I go on much further and before anybody else calls me out on it, JUnit theories are supported in JUnit 4. JUnit 5 is now the current version of JUnit, and JUnit 5 does not directly support theories in the same way. There are some other tools like JQuick that are part of this. Overall, this approach is called property-based testing. I know I had a property-based testing brief discussion with somebody in the class before the class started. So there's a slightly different way to go about doing this in JUnit 5 using tools like JQuick. Because JUnit 4 made it pretty simple to get the idea, I'm sticking with that for my examples, just so that you can get the idea. But recognize that JUnit 5, you're going to do it a little bit differently, but the concepts are going to be the same. So when we're building a theory, that theory is going to be based on this assume, act, assert model. And so we're going to have assumptions or preconditions. And those preconditions are going to limit the input values that we're selecting to make sure that we're only selecting valid input values. And then we're going to have an action. That action is going to do something. What's it going to do? Well, it's probably going to call the thing that we're testing. And then we're going to have postconditions or assertions, just like we had before, to check the result. So let's see how that assume, act, assert thing works. So if we go back and think about our adder class, we could put together a couple of theories, right? Some abstract thoughts about the adder class. And we might theorize, well, let's see, how does adder work? Well, if I add two positive numbers, then the sum is greater than either one. And if I add two negative numbers, then the sum is less than either one. I mean, those are two theories I could make about addition. And notice that those theories don't have anything to do with specific values. I'm just kind of identifying classes of input values and what their effects would be. So now I could take these two theories and I could write some JUnit theories to make sure that my adder function actually behaves this way. So what would that look like? Here's an example. First, I'm going to say run with theories. That identifies this as, hey, this is not just a regular JUnit class. This is a JUnit class running theories. Then I'm going to identify a whole bunch of possible inputs. This can be as many as I want, right? Whatever I want my set of inputs to be. So here I've simply selected a couple of integers, right? A couple positive, a couple numbers, a couple of negative. 0 is always a good number. Now I'm going to define a theory. Here's my first theory. My first theory is that the sum of positives is greater than either one. And we're going to pass in I and j. So if this theory is working on sums of positives, then I need some assumptions to limit myself to positive numbers. So I'm going to assume that I is greater than 0. And I'm going to assume that j is greater than 0. If I get passed in an I or a j that's not greater than 0, it's just going to get thrown out and the test is going to abort, not going to execute. So to get past these lines, we now know that whatever we got in, it's greater than, I and j are both greater than 0. So what's actually going to happen here is that when JUnit goes to run this, it's going to take all of the test values and it's going to put together automatically all possible combinations of I and j. So it's going to say I is 0, j is 0. I is 0, j is 1. I is 0, j is -2, etc. Then I is 1, j is 0. I is 1, j is 1. I is 1, j is -2, right? And it's going to make all possible combinations, and it's going to throw all possible combinations into this theory. But these assumptions are going to catch the ones that we don't want, right? Anywhere where I is not greater than 0 or j is not greater than 0, it's going to throw those out. So only the combinations where I and j are greater than 0 are going to get through here to the point where we act. That's going to specify our actions. So we're going to take I and j, we're going to pass it to adder.add, and then we're going to make our assumptions, and our assertions rather. And our assertions were, in our theory, that the sum of two positive numbers is greater than either one. So we're going to assert that sum is greater than I and that sum is greater than j. And now if we, sorry, one step too far, if we look at the sum of negatives, our other theory, the sum of two negative numbers is less than either one. So we're going to assume that I is less than 0 and that j is less than 0. All other test cases are going to get thrown out. We're going to actually act and add those two numbers and get the result. And then we're going to assert that the result is less than I and that the result is less than j. So this kind of theory or property-based testing, this can be very useful. It gives you a good way to automatically throw a whole bunch of different input combinations into a test. Right, so I define 1, 2, 3, 4, 5, 6 different input numbers here, 7 different input numbers. Yeah, I can do higher math, but addition is hard. 7, counting is hard. All right, I've got 7 input numbers. That means there's 49 test cases, right? 49 possible test cases, 7 times 7. So with a fairly small number of inputs, I can create a large number of test cases that then I can throw into these theories. So that really lets me explore a pretty wide portion of the input space if I do a good job choosing my test values. How do I do a good job choosing my test values? Tune back in a week or two when we talk about input domain testing. All right, our last lecture topic. I talked about JUnit being useful at the unit test level and the module test level and maybe the integration test level, but not being very useful at system test or acceptance test. So what is useful there? If I want to be automating testing at that level, what kind of tool do I want to be using? Yep, that's what I just said. One answer to that is Cucumber. Cucumber is a system and acceptance test automation tool. So in Cucumber, we're going to be writing system level tests, and we're going to be writing them in a language called Gherkin. And Gherkin is an English-like test specification language. I say that, but actually there's lots of variations of Gherkin. There's a Spanish Gherkin, there's a German Gherkin. I don't know what other versions of Gherkin there are, but there are lots of them. And it's a pretty simple language, but it gives us an opportunity to write our test specifications at a level that the non-development staff can easily understand, right? So the domain experts can understand this, right? The people who are part of our team who aren't the software developers, they're the people who understand how this kind of system is supposed to work. They can easily understand these tests. Our customers, if we, I said in the first week, if you want to teach about what you know, and most of my career has been in government consulting and defense consulting business, where we're working a lot with individual customers to give them exactly what they want. If you're doing commercial development, you're probably not going to have your actual customers looking at your system tests, but you've probably got a product owner or some surrogate for the customer, right? You've got some people on the program, in the project who've said, well, I know what the customer is going to want, right? I know what features we need to do to put this on the market and that people will want to buy it. Well, that person will be looking at your systems tests. And that person doesn't have to be a software developer. So when we write a Gherkin test consists of 4 things. It consists of a scenario, which is a very simple description of what it is that we're testing. Basically, we're naming the test. Then we have 3 keywords: given, when, and then. Given describes what's the precondition, right? What are all the things that have to be in place for this test to happen? When is, what is the actual stimulus or the actual input or the actual action that takes place to cause the system to do the thing that we want to test? And then lists the post conditions. What are the expected results or the expected after test state of the system? So again, we're writing these things at a pretty high level of abstraction, a level of abstraction that the system engineer, that the users, that the customers, that the test management, that our department manager can understand. So imagine we had an online ordering system, right? We're a little mini Amazon here. So I could have a couple of different scenarios here. So if I have an online ordering system, well, I probably need to support customer login. So my first scenario is named customer login, and the description, which is merely comment, is the customer logs into the account and is directed to his or her account. or logs into the system and is directed to his or her account, right? That describes the test. So what's our precondition? Okay, given that the ordering system is running and that the customer is on the test page or on the login page, right? Those are the preconditions for the test. We have to be here in order to make the test happen. Then when the customer does this particular thing, when the customer enters a correct username and password, that causes my system to do an action. And the result of the action is then the customer validates the login and the system validates the login and the customer is directed to the shopping search page. Those are my desired outcomes, my end result from this action. I might have another scenario where the customer picks something and adds it to their shopping cart. Okay, we'll name that add item to shopping cart. We'll describe it. The customer selects a displayed item and adds it to his or her shopping cart. So given that the system is running and that the customer is logged in and that the customer is on the item page for some particular item that we're going to use in this test, those are the preconditions. When the customer selects the item, right, selects to add the item to their shopping cart, that triggers the system to do something. And what's the result we're trying to verify? Well, we want to verify that that item is added to the customer's shopping cart and the order total is increased by $14.99 or whatever the correct price is, and the customer is given the choice to check out or continue shopping. So you can see that, I mean, this is a pretty high level test. This is a test that anyone on the product development team could understand. You don't have to be a software developer to understand this. You know, given, when, then, okay, yeah, I get that. That's pretty straightforward, pretty general. So you might be wondering, well, it sounds kind of like magic that I would be able to write when the customer selects add item and somehow the system is going to know what has to happen to make that happen. Well, you're right. That does sound kind of like magic. And guess what? There's no magic. So somewhere underneath the hood, things are happening to make that work. And it turns out that those things are actually implemented under the hood in Java. And I don't really care about you really understanding exactly what's going on here, but I just wanted to point out, you know, for those of you who are like, yeah, okay, that high level test language, that sounds great, but how does that really actually do anything? Here's how it does things. Because I will write Java and say the customer enters a correct username and password. That's one of the activities in Gherkin. When that activity in Gherkin is run, it'll actually call this Java method, and this Java method will actually make things happen. So the customer enters a correct username and password. I'm going to implement that by going to my graphical user interface and setting the text field username to johnsmith@test.com and setting the text field password to test password and selecting the button login. So that's how things actually happen under the hood with my Java code doing things. All right. I'm going to skip over that. Okay, yeah. Then the other side of that was the validations, right? The post conditions, the then, that's the same way. I specify a line here, the system validates the login, or the customer is logged in, which means either of those two phrases will map to this Java function. And this Java function will go out to the authentication agent, it'll find out who the validated users are, and it'll state an assertion that the validated users contains that user that just logged in. So this is where we turn the magic into implementation. We can also, in the step definitions, take arguments from Gherkin, right? We can kind of use this regex notation here and say, oh, match this to anything that says the customer is on item page with some number. And then when you see that, take that number and pass that number in as an argument. So this can actually get pretty sophisticated and pretty complex and pretty capable. I'm not going to dig into that all that hard, but I do want to mention just very briefly. So we end up kind of usually with this 4-layer structure for testing. And on the top, we have our Gherkin test specifications. Given this, when this, then that. That's this top layer. Then underneath that, we've got that second layer of Java tests saying, well, what given the user is logged in really means is do this in Java. And then often those Java functions are calling various different agents that we're writing separately. And then those agents are interacting with the system under test, right? So these agents are kind of making the connection between my test code up here and my executing system code down here. We don't have to care too much about what exactly those implementations are. It might be a simple function call. It might be a thing listening to a socket. I mean, it could be doing a lot of things. But these agents are just an abstraction layer that lets my test system talk to the system that I'm testing. All right, so quick summary, then we'll take our break. The best way we have to make testing efficient and effective and repeatable and all those good things we want it to be is to automate it as much as practical. And I say as much as practical, not as much as possible, because like I mentioned earlier, you don't have to look too hard to come up with tests that are so hard to automate, I really just shouldn't bother. We can use test frameworks like JUnit and Cucumber. That provides us simple ways to automate our tests. There's no magic going on here. The JUnit implementation is, only a few thousand lines of code. It's a pretty simple implementation. But having that there means that we can spend our expensive time, right? Our valuable expensive time. I can spend more of my time thinking about test logic, right? And that's a high value activity. And I can spend less of my time actually doing the work of, oh, I have to call this and I have to call that. Those test logistics, those are relatively low value. And if I can get JUnit to take care of some of those low value things for me, that means I have more time to spend on high value things, and that's good for everybody. And then the key caveat here is, while test frameworks can help me build tests, and they can certainly run tests and collect the results, and even to some extent verify that the results are correct, they can't tell me what I should test. They can't tell me what the test input should be. They can't tell me what functions I should call, what parts of the system I should test. That is the job of test design and of test criteria that we'll be talking about through the rest of the semester. Okay, so that takes us to actual break time. I've got 6:12. Let's take an 8-minute break. We'll convene back here at 6:20, and then we'll break up and go into class exercises. All right, so see you back here at 6:20.